All right. Well, thanks everybody for coming, and thanks Lauren for agreeing to come and give us a talk while she's on island. She's been out here for some Keck time. So she did her PhD at Berkeley, and while she was there, she observed a lot at Keck, but also she made the automated planet finder, which is a telescope at Lake Observatory. She made it automated. So there you go. That's and then 2 years ago, she moved to UDM. I'm not going to try and say it properly. And she's the inaugural Trottier postdoc fellow there at the Exoplanet Institute, iREx. She's going to talk to us today about exoplanets and stuff. Thank you.
Thanks so much for having me, Trent. It's a pleasure to be at Gemini. This is my first time visiting, so thank you all for coming. So I'm Lauren, and today I'm going to talk to you about how I use multi-planet systems as laboratories for understanding planet formation. So there are a few questions that motivate me. The first of which is which planets are common? And then what are the compositions of planets, especially small planets? I'm also interested in what properties are common in multi-planet systems. And I'm going to finish the talk with sort of like, as I described it at lunch, my fantasy lineup of how to use the Mauna Kea telescopes in the era bridging James Webb, or test to James Webb. All right, so let's get started. Which planets are common? You've all heard of the Kepler mission. This is a mission that was designed for exoplanet statistics. So it launched and just looked at a field of 150,000 stars for 4 years to count which planets are common. Here's an example showing some of the planets that Kepler found. So Kepler found over 4,000 planet candidates, many of which are indeed bona fide planets. This plot is showing planet radius versus orbital period. And as you can see, there are a lot of planets here. And over time, Kepler found more small planets at long orbital periods. By counting both the transiting planets that Kepler detected and figuring out which planets Kepler missed, we are able to do planet occurrence studies. So from Kepler, we've learned that planets close to their stars are very common. And 50% of sun-like stars actually have a planet the size of Earth or larger within 100 days. Now, as a reality check, we don't have that. Even though Mercury has a period of 88 days, it's smaller than Earth. So our solar system, compared to the Kepler systems, is quite barren at close orbital periods. We've also learned that small planets are much more common than large planets. About 1 in 5 sun-like stars has an Earth-sized planet within the habitable zone. And indeed, a large fraction of stars have small planets. About 50% or so of stars have a planet smaller than Neptune that is close to the star. The commonality of small planets extends to M-dwarfs as well. So while we know that small planets are common from Kepler, we don't know their compositions. And this is because although these planets are very common in the galaxy, measuring their masses is challenging. We conducted a study of the masses and densities of 65 small exoplanets. So here what we're plotting is planet density versus planet radius. And in making this plot, we detect that there is a peak planet density at a size of 1.5 Earth radii. For planets that are smaller than 1.5 Earth radii, planet density tends to increase with increasing planet radius in a manner consistent with the compression of rock, meaning that these likely have rocky compositions. Above 1.5 Earth radii, planet density decreases with increasing planet radius, which we interpret as an increased admixture of volatiles. So in recent years, we've made some more progress on this topic. We've just published the California Kepler Survey, which is a new exoplanet parameter study based on getting Keck-HIRES spectra of 1,305 Kepler host stars with 2,025 exoplanets. So the goal of this study was to get a consistent catalog of stellar properties of the Kepler planet hosts. And within this catalog, also get better stellar parameters that then allow us to update planet parameters, such as planet radius. So this study was conducted with Keck-HIRES. It was done by these folks here, many of whom you might know. Can anyone recognize where this photo was taken?
Is it the IFA courtyard?
Yeah,
Okay.
yeah, in Manoa.
So,
Yeah,
so that was, well, you were at Berkeley when this was taken? And
yeah, this was
But
my
Andrew
final
was at-
year. Yeah,
Andrew
but
was at
we,
Hawaii.
yeah, we commuted to Hawaii. Yeah. It was a fun commute. Anyway, so it took us about 3 years to collect the data. We didn't sleep much, but we went to Hawaii. So here are some example spectra from the California Kepler survey of stars of different temperatures. This is the magnesium B triplet. And you can see the quality of the spectra allowed very precise stellar characterization. The spectra have a typical resolution of 60,000 and a signal to noise of 45 per pixel. And we get all sorts of great properties, as you can see here. And in particular, we get precision stellar parameters such as mass with an uncertainty of just 5% and stellar radius with an uncertainty of 10%. So what that let us do is propagate that smaller radius uncertainty to the sample of Kepler planets. And what we found is that small planets cluster in two sizes in a manner that we believe is linked to their compositions. So we see two bumps in this distribution, one of which for the small planets might be rocky super-Earths, and then for the larger planets, larger than about 1.8 Earth radii, this second bump is volatile-rich sub-Neptunes. So exploring the distribution of this gap in planet radius is going to teach us the physics of how planets acquire and or lose their volatile envelopes. And I guess I can talk more afterward if you're interested about future follow-up studies for this discovery. But I'm going to transition now to talk about other products from the California Kepler survey. I'm using the CKS sample to explore the demographics of multi-planet systems. So in these systems, we can explore fundamental stellar and planet properties, but we can also compare each planet to its neighbors, allowing us to gain additional physical insight. So just a few weeks ago, we had a press release, and this is a summary slide of my press release for a scientific audience. The punchline is that planets in the same system have similar sizes and regular orbital spacing. So what I'm showing here is just that if you take a pair of planets and plot the outer planet size versus the inner planet size for each pair in a multi-planet system and repeat over many systems, there's a correlation. And the same thing goes for planet orbital spacings. And I'll describe this in more detail in just a moment.
Where would the solar system's planets be on that plot?
They are not on this plot, but they would have more scatter than what's observed. So because of the sort of tongue-twisting nature of this result, we nicknamed it the peas in a pod result, because peas in a pod demonstrate the same pattern that we're looking at. So this discovery was actually sort of a happy accident. I was just looking at the properties of the multi-planet systems from the California Kepler survey. So just quickly, this was 355 multi-planet systems with 909 transiting planets. And I wanted to get a sense of just an overview of what I was looking at. So I made this plot, which is showing the architectures of all the systems that host 4 or more transiting planets. They are ranked by stellar mass, with high stellar masses at the top and low stellar masses at the bottom. And the star names are on the left. And oops, it's cut off at the bottom, but semi-major axis increases toward the right. The planet sizes are drawn to scale. And yeah, I guess you can't see the key on this plot. This got screwed up. But So these smallest planets are roughly Earth-sized, and then these largest planets are about Jupiter-sized. And the equilibrium temperature is shown as a color bar. One nice aspect of CKS is that because we got much better stellar temperatures and radii, planet equilibrium temperatures are much nicer now. So just looking at this, I was surprised to find a pattern. So I'll zoom in a little bit and see if you see the pattern. Give you 3 or 4 seconds to think about it. So I see that planets in the same system tend to have similar sizes, which I've highlighted in these pink boxes. Now, it's nice to have this observational result, but since we're scientists, it's good to be quantitative. So to better quantify the result, we took pairs of adjacent planets in the same planetary system and plotted the outer planet size versus the inner planet size. So you can see that there's a high correlation, a high Pearson R correlation between the sizes of adjacent pairs of planets. But is this correlation really astrophysical, or could it be brought on by observational bias? To test the role of observational bias, we designed a bootstrap test. So for each observed system, we used the observed stellar property and observed orbital periods of the planets, but then drew the planet radii at random. The way that we drew each planet radius did not depend in any way on the size of the previous or the next planet. So this is a test of the null hypothesis, which is that the planet sizes in the same system are not at all correlated. Then we removed any planets that were too small to detect in each system.
Are you worrying about the fact that not all planets are going to transit in these systems? Most do, but you could potentially have a gap where a planet is not quite aligned enough for us to see.
No, we're just counting transiting planet multiplicity, because we did see this pattern with transiting planets. So we didn't vary the inclinations of the planets at all. All right, so here's one example of our bootstrap trial, and we see no correlation between the planet sizes. So the bootstrap trial did not reproduce the observed correlation, which again is here. No correlation in the bootstrap, correlation in the real systems.
Sorry, so are you using fully simulated planets, or are these, you're taking planets, the real population, and redistributing them?
Drawing at random from the observed population, but we also tried drawing from a log normal distribution and uniform distribution. And they all basically looked like this, that if you draw planet sizes at random from any not ridiculous distribution, you get something like this.
So is this, for your sample, it's not all of the Kepler planets, correct? You're using subsample you guys have spectroscopic observations for?
Yes, but we got spectra of almost all the multi-planet systems. This is 355 systems.
Right. And most of these are compact, correct? Are the
Yes.
out of percentage of these, how many of those are the number of planets, the small planets that are all within like Mercury's orbit? Is that most of
most of them, yeah. I mean, that's most of what Kepler found. So that's what we're dealing with. You'll see more of that in a moment. All right, so we repeated the bootstrap test 1,000 times, and none of our trials came close to reproducing the observed correlation in real planetary systems. So we rejected the null hypothesis and concluded that the similar sizes of planets is actually an astrophysical result about planetary systems. I also noticed that planets in the same system tend to have regular orbital spacings. And indeed, they are in these really compact architectures. But if you look at where one planet is and then in the next planet, you can very often roughly predict the orbital period of the third and fourth planet in this diagram. To quantify this pattern, we took all the systems with 3 or more transiting planets. We compared the ratio of orbital periods of the innermost pair on the x-axis to the next pair out on the y-axis, iterating through all of the pairs, or I guess through all of the triples in each system. So of course, again, there's significant correlation here, a high Pearson R value and low p value. And when we construct an analogous bootstrap test, we do not reproduce the correlation. And again, repeating 1,000 trials, we don't ever reproduce the observed correlations, significance, and strength. So again, we conclude that this regular orbital period spacing is astrophysical. So the next question that I asked was whether there's a correlation between the planet sizes in these compact systems and the orbital period spacing. So for each pair of planets, we plotted their period ratio, which is on the x-axis, and their average size on the y-axis. And you can see there's significant structure to this plot, where the smallest planets are all very close together. And then the slightly larger planets can be a bit further apart. And this is interesting because even these smallest planets would be detectable if they had larger orbital period ratios. So this is, again, not the result of some detection bias. Additionally, I noticed this feature on the left, which is that regardless of planet size, the orbital period ratio of the outer planet to the inner planet is larger than 1.2, which I think is potentially related to Lagrange instability, which is where resonance overlap causes orbits to be chaotic before Hill instability has a chance to set in. So this is from a paper by Keck in 2013. I recommend checking it out. I think this is interesting because everyone always talks about Hill stability as the criterion for how close you can put two planets to each other. But with these guys right here, would be Hill stable much closer together than we currently observe them. So perhaps this period ratio at 1.2 and Lagrange instability is the reason that small planets don't get closer together than we observe them. Okay, so we found 3 patterns to reproduce in a population synthesis. The first of which is that planet sizes in individual systems are correlated. The second of which is that planets in individual systems have similar spacings. And the third of which is that across all systems, there seems to be a relationship between planet sizes and spacings that we don't understand. So I put on my theorist hat and read some old theory papers. Take this with a grain of salt. I'm not a theorist. But I was reading this paper from 1993, which is before the discovery of the first exoplanet. And what Lissauer and Stewart said is that from runaway growth, they expect planets will form at regular intervals in semi-major axis, which is kind of interesting. So a few years later, Kokuba and Ida wrote another paper and predicted that protoplanets with the same order masses are the inevitable outcome of planetary accretion. And I thought, wow, that's great. These papers from like before we had a transiting planet happen to describe this pattern in the California Kepler survey multis. So there are some issues with trying to describe mature planets with theories about protoplanets, which are much less massive than planets that we see today. But perhaps there's some way in which these compact multis have preserved the early structure of planet formation. Or maybe there's some other planet formation mechanism that explains them. It's going to be up to the theorists to reproduce these patterns. But I think this is one intriguing possibility. Okay, so this part of my talk is preliminary. This is a new paper that I'm working on. So the peas in a pod paper was great. We learned a lot about multis, but now I want to look at how the Kepler multis that have multiple transiting planets compare to systems with one transiting planet. So just to review some terminology here, when I say multi, what I mean is a system that has multiple observed transiting planets. And when I say single, I mean a system with only one observed transiting planet, but there could be other non-transiting planets. We just don't know about them because they don't transit. So I was interested in which factors that we've now measured correlate with the number of observed planets. So in particular, how do the host star properties compare to the multiplicity of planet systems? And how do the planet properties compare? So first of all, host star properties. This is just a histogram of the masses of host stars of the CKS singles and multis. Those singles are in red, multis are in blue, and there's no significant difference in the distribution of the masses of the CKS singles versus multis. Okay, what about metallicities, right? Maybe more metallicity could help you build more rocky cores or something like that. But it turns out that there's no statistically significant distinction between the host star metallicities for singles versus multis either. We also looked at stellar age, effective temperature, projected stellar rotation, a bunch of stuff. It's all histograms that basically just look like this. We didn't find any stellar property where there was a significant difference in the distributions for the host stars of one versus multiple transiting planets. Okay, so what about planet properties? When we turn to planet sizes, we begin to see some differences. So the distributions of planet sizes are the same for small planets, with both multis and singles showing this gap in planet radius at about 1.8 Earth radii. However, giant planets tend to be single, which we can see in the tail of this distribution and in the gap in the cumulative distribution function. The orbital distances of singles and multis are also slightly different. The distribution of multis is a little bit more peaked at 0.1 AU, and the singles has slightly larger tails. So this is a little bit perplexing, but when we look at radius and semi-major axis together, these patterns make a little bit more sense. So we can see that for the most part, singles and multis are indeed occupying the same part of parameter space in the period radius diagram, but hot Jupiters are almost always single. And that explains why there were more large giant planets, and it also slightly explains the distribution in semi-major axis differences. We also see a population of hot Earths that appear to be single. So both of these populations were already known. These aren't new discoveries, but it's nice to see them show up again in a statistical survey. So in summary, host stars are not different based on the number of transiting planets. The planet properties are slightly different, but really mostly just for these very, very close in hot Jupiters and hot Earths. So this is interesting and a little bit troubling to me, because in the TESS era, when we get transit photometry from a star and detect a transiting planet, and we want to know, should we keep studying this star to look for another planet? There's no host star property or planet property that's going to be predictive of whether or not there's another transiting planet. We'll just have to figure out some other way to choose. All right, so I guess one other interesting thing about the similarities between the Kepler singles and multis is that if the stellar properties are so similar, maybe that means that the singles became singles later in planet formation. So perhaps there's some process like planet-planet scattering that results in higher mutual inclinations between the singles, but that happens well after stellar formation. So one thing that I'm interested in doing to try to solve this problem is an ongoing project called the Kepler Giant Planet Census, in which we are investigating what is the connection between giant planets and these interplanetary systems. So Kepler taught us very little about long period planets. Again, here's this like waterfall plot. And you can see that most of these planets are all within 1 AU just because of the Kepler sensitivity. So we don't know from Kepler whether these compact Kepler multis that are so common have Jupiter analogs in a greater or lesser frequency than field stars. So what I'm doing is using radial velocities to probe which systems that have one or more small transiting planets have long period giants. So these are some of the systems that we're following. The stellar names are given here, and the dates of our observations are on the x-axis, and the number of observations are here. This is 48 stars, many of which have baselines going back to 2009. And with this survey, we will be sensitive to Saturn mass planets at 3 AU for 50% of our stars. When the survey is done, we'll be able to better answer what are the masses, orbital periods, and eccentricities of any giant planets that we find. How do the properties of giant planets differ around the multis versus the singles? And maybe that'll help teach us how giant planets are influencing the formation of sub-Neptunes and terrestrial planets.
What's the accuracy in meters per second? Or is that 3 Saturn?
I mean,
Saturn
that's a stellar dependent property. For most of these stars, so most of these stars these are all Kepler stars. So their brightnesses range from maybe about 10th magnitude to 12. So for the best ones, we can get 2 meter per second accuracy. For the worst, maybe like 3, 4.
And so this sample is like half multis and half singles or something? Or,
Yeah,
okay.
yeah. And it's, yeah, and for some stars, we're pretty much complete already, and for other stars, we aren't. So it's sort of a half-baked survey at the moment. We'd like to finish it. All right, so I'm going to switch gears a little bit. The work I've described in this talk so far has been statistical, but to actually gain insights about how planets form, it's often useful to study individual planetary systems. So this is WASP-47, a laboratory with a hot Jupiter. Hot Jupiters are rare. They only occur around 1% of stars. But WASP-47 is especially rare because it is the only known hot Jupiter with companions. Here are the 3 transiting planets in the WASP-47 system. The hot Jupiter, planet B, was discovered with ground-based photometry in the WASP survey. When the revamped Kepler satellite K2 stared at the star for a few years later, the superior space-based photometry found 2 additional planets, both of which are smaller than Neptune. So you're going to have to read the y-axes here to figure out which one is the giant planet and which ones are the small ones, because they're not all to the same scale. So the hot Jupiter is the one in the middle. It's got a period of 4 days. And then there's a 1.7 Earth radius planet interior to it with a period of less than a day, and a 3.6 Earth radius planet exterior to the hot Jupiter at 9 days. The transits of WASP-47 exhibit transit timing variations due to the planet gravitational interactions. By forward modeling the transit times with an n-body code, we explored how well the observed transit times constrain the planet masses. Unfortunately, large degeneracies between the planet masses and orbital periods inhibited a precise mass solution for some of the planets. So in this system, RVs were able to come to the rescue, and we used radial velocities from 4 different spectrographs, including Keck-HIRES, to characterize the planet masses. The full time series of RVs is shown on the left, with residuals down below. And on the right, those RVs are phase folded to the orbital periods of the individual planets. In addition to the 3 transiting planets, there is a long period planet at about 600 days that has significant eccentricity. With the combined fit to the RVs and TTVs, we get the masses and eccentricities shown in these blue boxes, which are much more precise than what you saw before. So indeed, now we can clearly state that the transiting hot Jupiter, which is actually Jupiter mass, is an order of magnitude more massive than its neighbors, which are roughly 10 Earth masses. So how did this hot Jupiter manage to form without disrupting these much smaller neighbors? I think WASP-47 might have formed in 2 stages. This is just one theory again. So in stage 1, giant planets get to form and migrate in a gas-rich disk, sculpting the planetesimal disk. And then in stage 2, when the disk becomes gas-poor, the planetesimals accrete and form subneptunes with about 1% of their mass in gas, which is consistent with the observed densities of these planets. So because the small planets are both low mass and have gas, they do have to form before the gas disk disperses, which means that the hot Jupiter this guy, the hot Jupiter, has to park in place with basically 0 eccentricity before the gas disk disperses. So this actually rules out high eccentricity migration as a method for forming these planets. To further test how the WASP-47 system formed, I am proposing to get observations of WASP-47b and transmission spectroscopy with NIRSpec. So many other hot Jupiters will also be observed in the James Webb GTO time, allowing a thorough comparison between this particular hot Jupiter and the more garden variety hot Jupiters without companions. In particular, we hope to test whether the C to O ratio is different between this planet and the other giant planets, and maybe that would help teach us whether it formed inside versus outside the snow line. And we'd also like to measure the metallicity in the atmosphere of this planet, which is interesting because the host star actually has a very high metallicity of 0.4 or something.
I have a quick, can you go back to your theory scenario? I didn't understand, you didn't show us, right? Don't you need the small planets on either side of Jupiter? So
this was like a generalized cartoon that was not actually supposed to reflect the WASP-47 system, but I should do a new cartoon that better describes this, because you do need to make one little one on the inside and one little one on the outside. And then also a big one with high eccentricity, which has to come after the gas disk disperses, which means it can't be kicked by the transiting planet because that one had to be parked. So we don't really understand how the outer planet got its eccentricity. There probably was another planet in the system, or might still be another one. Question?
So the innermost one is, if I did the density right, that's a terrestrial, and the outer small one is
the inner one. No, the innermost planet it likely has a very thin volatile layer of some high mean molecular weight substance, kind of like 55 Cancri E, which is also
what are the mean densities?
I don't have the densities written here, but it's at about the rocky planet boundary. So our mass uncertainties are too large to definitively say whether it is a rocky planet or whether it is a mostly rocky planet with a very thin volatile envelope. It has a radius of 1.7 Earth radii, which is very near that transition between rocky and non-rocky interiors, but its orbital period is just 0.8 days. So it can't hold on to any hydrogen or helium. So any volatile layer that it's retaining has to be a high mean molecular weight layer. But we need to improve the radial velocity mass of this planet to be more definitive about that. Andrew Vanderberg actually wrote a nice paper recently with combining HARPS North RVs into the mix and voted on it has a volatile layer side of the vote, but I think it's still open for more measurements. Okay, so a totally different planetary laboratory that is near and dear to my heart is TRAPPIST-1, which is a late M dwarf orbited by 7 Earth-sized planets, 3 of which are in the habitable zone. The innermost TRAPPIST-1 planets were discovered with ground-based telescopes, and then an extensive Spitzer campaign revealed additional transiting planets, as you can see in this light curve. The TRAPPIST-1 planets are Earth-sized, as shown by their transit depths, but the masses of the planets are not well understood. This is because only a few transits have been observed, and many transits are needed to understand the complicated patterns in transit timing variations that will actually reveal information about planet masses. So here's a measure of the transit timing variations over time for TRAPPIST-1G, and there are only 6 data points trying to constrain a very complicated transit timing variation model. As we just discussed for the innermost WASP-47 planet, it's especially important to get good masses of the smallest planets because ultra-precise masses are required to distinguish rocky planets from planets with a volatile envelope. In this plot of planet radius versus mass, you can see broad uncertainties in the masses for some of the TRAPPIST-1 planets that span various theoretical composition lines. So TRAPPIST-1e here has a mass that's consistent with non-existent or zero density, but also consistent with a rocky composition. So this is especially problematic because we would like to observe a few of these habitable zone TRAPPIST-1 planets with James Webb NIRISS to get transmission spectroscopy and details about their atmospheres. But we don't even know if they have atmospheres for some of them. So to mitigate this problem, I've been leading 2 CFHT programs to measure more transit times to constrain the TRAPPIST-1 masses. We've been using WIRCAM in the KS band and MEGACAM in the I band to get transits of the outer TRAPPIST-1 planets. And we recently had an achievement with MEGACAM where our detection of the TRAPPIST-1D transit on August 20th was the first time that MEGACAM was used to measure a planet transit. So the folks at CFHT are really excited because MEGACAM is their most used instrument and they're so happy they can do transit science with it. So this is a preliminary data. I basically just wrote the proposal and argued for telescope time, but the people doing the real work are my colleague Loïc Albert and François René Lachapelle, who's a graduate student. So François René is actually doing the, the photometry and getting these nice light curves and trying to fit them to get transit properties. And eventually what we'd like to measure is what is the center time of this transit, which is then the one number with uncertainties that goes into this awfully complicated plot that we'd like to better constrain. So as you can see from this plot, we would really like to just observe every transit that we can. We're doing our best.
And that's why you're using the 2 instruments, I guess, right? So that,
yeah,
unlike Gemini, they go
Yeah.
on and off the telescope. So
That's right.
Just to catch a transit, you have to use different cameras.
Exactly. We want to catch all the transits. And we actually joined a large international follow-up program that's using telescopes at like all the longitudes. We have a spreadsheet, a Google sheet with like each telescope name and then in parentheses a number showing its longitude so that we can keep track of who can see what. Anyway, this leads me into the final part of my talk, which is what should we do to learn more about planet formation? And specifically, what can we do in the James Webb era? So I'm interested in bridging the gap between TESS and James Webb. In combination, these telescopes promise to revolutionize our understanding of exoplanet atmospheres. TESS is an all-sky photometric survey that is dedicated to finding transiting planets around the nearest and brightest stars. And the name of the game is find the planets with TESS. They're going to be bright, which means we can point James Webb at them and study their atmospheres. One possible outcome of this study in the best case scenario would be detecting water and or carbon species on super Earths, which would be great. But there's a big problem, actually a few big problems, which can be summarized in the fact that both of these missions say that ground-based support is really important for achieving their goals, but neither of them have a comprehensive plan of how to use ground-based support. So TESS is going to find these exquisite planets, and we're going to need to do a lot of ground-based observing to get ready for James Webb observations. So what kind of measurements will we need to take? I think one of the biggest gaps to fill is that because TESS is only observing planet transits, it'll only get planet radii and not planet masses. This is a problem because to characterize the composition of a planet atmosphere, you need to know the atmospheric scale height, which is shown here. Right? So you have the total radius of the planet, but the atmosphere is only some portion of that. And based on the mass of the planet, that's going to affect the scale height of the atmosphere. So we'd really like planet masses to know how much atmosphere the light is passing through. Fortunately, on Mauna Kea, we already have Keck-HIRES, which is delivering accurate and precise masses of small transiting planets. This is the Kepler 10 system, which is around a bright star comparable to some of the stars that TESS will observe. And there's an inner transiting planet and an outer transiting planet. We've got precise masses and densities for both of them. The inner planet turns out to be rocky at this density and size, whereas the outer planet, even though it has a sort of similar density, is larger, so requires a significant volatile envelope. But the sort of one of the issues with this is it took like 200 radial velocities to gather this information about planet compositions. So if you're doing the math, if TESS actually launches like when it's supposed to, and James Webb launches when it's supposed to, we've got like a year of lag time to catch up and get masses of any new planets before James Webb is up. So we've got to get on this. Fortunately, there are some new instruments coming online right here on Mauna Kea. In particular, Spirou on CFHT will measure precise RVs for late M dwarfs. And here are some Keck RVs of a standard star M dwarf. And hopefully we would be able to benchmark Spirou and IRD on Subaru and any other new near-infrared spectrographs against standard stars. And ideally what I'd like to do is get measurements on all these instruments on like the same nights, so we can actually see how is the RV jitter varying in the infrared versus the optical. Okay, so masses will be great, but there's another problem, which is that TESS has a step and stair pattern that results in the majority of targets only being observed for 27 days. Now this is a problem because most planets from Kepler have orbital periods of about 10 days, but you need 3 transits to actually measure the orbital period, or even if you want to measure it just roughly. So for any planets beyond about 9 days, the orbital ephemerides will be really uncertain. And we need photometric follow-up to get correct orbital periods for these planets, just so that we know when to point James Webb at the star to observe a transit. This is especially going to be a problem if TTVs are present, because even though sort of the gold standard for knowing a transit period is to see 3 transits and then just fit a line, if you're sampling some part of a large amplitude TTV curve, you could be way off. So we need photometric follow-up. We're doing that already. It's going well with TRAPPIST-1. We want to do it again, especially for the most exciting TESS stars where we'd like to eventually get James Webb follow-up. So we're going to need to get a lot of additional photometry before even pointing James Webb. Another issue is that TESS has wider pixels and lower sensitivity than Kepler, which makes false positives more likely. Kepler had a pixel size of 4 arc seconds. TESS will be 10 arc seconds, which leaves extra room for a background eclipsing binary to slide in and masquerade as a transiting signal. Fortunately, we have some great expertise here on Mauna Kea about doing direct imaging. In particular, RoboAO will do nightly imaging from the UH-88 telescope, and quickly identify companions. So in one night of observations, over 100 stars can be observed with direct imaging. You can see some of them and have companions. So hopefully between Trent and Christoph and all of the direct imaging expertise up here, you guys are gonna have a field day and write like tons of publications about all of the false positives that TESS finds. Let's see, one other false positive follow-up that we can do is to identify double-line spectroscopic binaries with high-resolution spectrographs, such as iRES, Spirou, IRD, and even Ishell should be good at this. So if we see a double-line signature, that would be indicative of a binary and not necessarily of transiting planets. So in summary, we need ground-based TESS follow-up in order to get the most out of our James Webb observations of the best planets, especially the best super-Earth planets. Fortunately, Mauna Kea is rich in facilities that can lead the charge, and I really hope that folks here will take up the banner and do lots of great exoplanet science in the James Webb era. So I'll put my summary up there and say mahalo.